Welcome to Pre-Calculus. Today we will determine the relative extrema of functions, focusing on finding maxima and minima, as well as recording intervals of increase and decrease. Let's take a look at a total of 4 examples. We'll look at 2 examples to begin. So we'll head to our notes screen. And here's our first function. So we want to graph the function by creating a table of coordinate points. And then once we've got that graph, we want to determine the relative maxima and relative minima of each function. Record the intervals of function increase and decrease. And we'll use our maxima and minima to do that second task, to find the intervals of increase and decrease. Well, first things first, let's graph the function. So as we've been doing, to graph a function, we want to begin by creating a table of coordinate points. So like we've seen in past examples, we're going to put our x values in that left column. And to keep things centered, I'm going to start with 0 in the middle and -1, -2 to the left and 1, 2 to the right. Maybe we'll expand it, but that's a good place to start. And what we're looking for, what are the y values? How do I determine a y value given these x values and this function f of x equals x cubed minus 6x? So let's evaluate manually and see if we can graph this function that way. So my first value is -2, so I want to calculate f at -2. So that's going to be replacing every x value in the function with -2. So -2 to the power of 3 minus 6 times -2. -2 to the power of 3 is -2 times -2 times -2, which is -8. And then -6 times -2 is plus 12. And -8 plus 12 is -4. So we got a coordinate point here, -2, -4. We'll graph that in a moment. Let's collect our other points. So we'll keep on going with our manual evaluation. So here I'm replacing all the x's with -1. So -1 cubed minus 6 times -1. -1 cubed is -1 times -1 times -1. That's -1. -6 times -1 is plus 6. -1 plus 6 is 5. So that function has climbed a lot from -2 to -1. Started with the value of -4 at -2, and then it's at +5 with -1. At 0, f at 0. Now each term here has an x in it, so this is 0 cubed minus 6 times 0. And remember, anytime I multiply by 0, I get 0 back. So this is 0 minus 0, which is the point that we call the origin, 0, 0. Let's calculate f at 1. So 2 more of these evaluations left. So that's 1 cubed minus 6 times 1. 1 cubed, 1 times 1 times 1 is +1, minus 6 times 1 is 6, -5. So the next value we've got is 1, -5. And the last substitution is 2, +2. So we'll evaluate 2 to the power of 3 minus 6 times 2 equals 2 times 2 times 2, that's 2 cubed is 8. Minus 6 times 2 is 12. 8 minus 12 is -4. And it looks like I've made a mistake on my very first calculation. So those who had caught it, you've been waiting patiently. -8 plus 12, not -4, but +4. So let's correct that so we get an accurate graph. And the last point that we saw was 2, -4. Well, let's graph this function. At -2, we saw our value was at 4, the corrected value. -1 is at 5. We go through the origin, And then at positive 1, we're down at negative 5. And then positive 2, we're at negative 4. Now, if I'm going to sketch this graph, it's going to approach this value at negative 2, 4 from below. It's going to go up, then come back down, head through the origin, and then descend and ascend. So that's our first task. And essentially what we've done is we created a table of values to give us a framework for the graph. Now, let's tackle our second task. We want to determine the relative maxima and relative minima of each function. So one of the things we need to say is, how would we define a relative maxima? How would we define a relative minima? These are coming from Latin, and basically what a maxima says is what's the highest point on the graph. And you can think about what a minimum might be. That's really the minimum. What's the lowest point on the graph? So see if you can predict, looking at this graph of x cubed minus 6x, what would you say is the highest point on the graph? My attention is drawn to this point in quadrant 2 that I'm putting in red as the highest point. Now, notice we call it the relative maxima. And the idea is that this is a high point on the graph, but it's not what we would call the absolute maxima, because if I trace over, a lot of these points on the right-hand arm of that function are higher than that point that we found over in quadrant 2. So it's not absolutely the highest point on the graph, but it represents a hilltop. So that's why we call that a relative maxima. Let's go ahead and just write that there. Now, as I record this, see if you can predict, what do you think is the relative minima? What do you think is the lowest point on the graph? Definitely, that lower trough, that valley there in quadrant 4, we would identify as the relative minima. Just like with the relative maxima, we say it's relative and not absolute, because if I traced over, there's a lot of values on that lower arm down in quadrant 4 that have a lower value than that trough, but it does represent the bottom of a valley, and so we would call it the relative minima. So we want to find those coordinate points. What's the coordinate point here at that top of the hill, the relative maxima? What's the coordinate point down here at the bottom of that valley, that relative minima? Well, there's some stuff that we could do algebraically, but again, we have to consider what tools do we have in our tool belt? What would be the most efficient way to find those coordinate points? So I'm going to head over to the calculator, because I have a feeling that I can use the calculator to really efficiently find those, the relative maximum and the relative minimum. Now to do that, I'm going to put my cursor there in the entry and type in f parentheses x, f at x equals, and then I'm going to put that function x to the power of 3 minus 6x. Then I'm going to close down the keypad so we can see our graph. And definitely this is the graph we just put on our coordinate plane. Now, the nice thing about this Desmos is that it will label already and tell us the coordinate for our relative maxima, and so I'll go ahead and click that, our relative minima. So I'm going to record those points. So over there on quadrant 2, this upper point, the high point on the graph is negative 1.414, 5.657. And the low point's at positive 1.414, down there at negative 5.657. I've recorded that, and I'm going to head back to our notes to write those in. So again, this is negative 1.414, comma, 5.657. And the low point down here, the relative minima, is negative or positive 1.414. X value is positive, negative 5.657. So we completed that second task. Our last task is to record intervals of function increase and decrease. And what we'll do is we'll use those two, the relative maximum and the relative minimum, to say what are the intervals of increase and decrease. So I'm going to record down here at the bottom part of this graph the intervals of increase. Now what we're saying when we say intervals of increase is we're saying over what x values is the function going up. So I'm just going to trace them in the green. I think it's this left side all the way up there, but past that hill it's going down. So I'm not going to highlight this middle section. But when I reach the valley, the relative minima, it all of a sudden starts to increase again. So the way I'm going to write this is in interval notation. So from the left side, and again, we're describing the x values where it's doing this increase. So it's from negative infinity on the left all the way up through the x value of my relative maxima, so negative 1.414. We'll skip that middle section because it wasn't increasing over that middle section. And then I'm going to pick up at the relative minima's x value and say that it increases from that point all the way over to x's positive infinity. To finalize this question, all we need it to say is, where is the function decreasing? What's my interval of decrease? And we'll record this in the purple color. And really what we need to highlight is that middle section of the graph. From this high point, the relative maxima, the whole function is going downhill to that relative minima. So to describe that, we're going to start at the x value of the relative maxima, negative 1.414, comma, to the x value of the relative minima, 1.414. And that completes that process. We graph the function from a table. We identified the relative maxima and the relative minima using Desmos to find those coordinate points of the hill and the valley. And then we recorded the places, the x value intervals where the function was going up, that's the green parts, and the places in the x values where it's going down, that middle section highlighted in purple. Let's take a look at a second example. So here we've got a function f of x equals x to the power of 4 plus 2x cubed minus 2x squared minus 3x. So again, our task is the same. We want to graph the function by constructing a table of values. And then we want to graph it, identify maxima, minima, and then record the intervals of increase and decrease. Now the previous function we evaluated manually because it was a simple enough polynomial. This polynomial has 4 terms. So I am going to head over to the calculator to utilize that efficient tool. So as we pull up Desmos, I'm going to clear out that first function. And we'll type in f of x equals x to the power of 4 plus 2x cubed minus 2x squared minus 3x. And that gives us this kind of a U-shaped function with a dimple in the middle. So I'm going to create a table of values. And I think I need to center it around the x value -1. I see that's kind of the center of the graph. So I'm going to back up to -3. So I'm going to record those points: -3, 18, -2, -2, -1, 0, 0, 0, 1, -2, and 2, 18. Let's head back to graph this function. So that same table of values I'm going to record here. So we had from -3 through 2. Zero, 1, and 2. So -3 was 18. -2 was -2. -1 was 0. 0 itself was 0. And remember, in here we had 0.5. Should go catch that point. We'll head back in a moment. So I'm going to just keep that kind of in mind, because I see that there's a hill in between those two values. But at 1, we're at -2. And at 2, we're back at 18. So let's graph what we've got here. So -3, 18 is way up in the sky. So I'm not going to graph that one. I got it represented on my table. But at -2, we're at -2. At -1, we're at 0. 0 is at 0. 1 is at -2. And then 2 is up at 18. So we'll graph this function. So I'm going to pick up. And what we've got to consider is that we are descending from 18 at 3. So it's coming from above, hitting that point, and it goes a little bit further down, it comes back up. Kind of looks like a tooth. And there's the rough shape of our graph. So we've completed that first task. We've graphed the function by creating a table of coordinate points. At this time, I want to identify points on the graph that would be either relative maxima or relative minima. So let's start with the relative maxima. And I'm going to give you a moment just to consider that graph. Where do you think the relative high place on the graph is? Where is there a hilltop? Excellent. So that place where x is 0.5. And then let's identify the relative minima. Where are the low spots on the graph? Where are the valleys? Good. So it looks like on this example, I've got one maximum, relative maximum, and two relative minimas. So just like we did on that first example, I'm going to go back to Desmos to find those points from the graph. So remember, to find it, you're just going to click on that high point. So definitely we're at -0.5, and that's the value 0.813. Then I'm going to find this lower point, -1.823 and -2.25. And on the other side, it's real symmetrical. It's 0.823 and -2.25. So those are the same low points in terms of the y. Okay, so we've got our values. Let's record that on our graph. And for your homework, what you can do is you can actually record these directly on your graph. So that maximum is -0.5, comma 0.813. That's the maximum. And again, we would say it's relative because there's all kinds of other points on the left and on the right that are taller or higher than that, what we're calling a maximum. But it is the top of a hill. So we call it the relative maximum. Down here below, let's record those values. So this one on the left is negative 1.823, comma, negative 2.25. And this on the right is 0.823, same y value, negative 2.25. Those are our minima. Notice if you got two of them, that's plural, so you use that A. If you only have one, it's a minimum. So we only had one hilltop, so we call it the maximum. If you got two, they're the minima. That's completing our second task. To complete this question, all we got to do is record the intervals of function increase and decrease. So like we did on that first example, what I want to do is pick up with the green to describe intervals of increase. And first, what I want to do is just highlight them in the green. So this left arm is not increasing. As x's go up, it's going down. But once we reach the valley, there's an increase from negative 1.823 up to the x value of that hilltop, which is negative 0.5. The next interval is a downhill slope all the way down here to this right-hand minima at 0.823, but from 0.823 until we have another interval of increase. So it starts at 0.823. See if you can predict where does that interval end. Good, it goes forever. So we would say this interval goes to infinity on the right. Let's complete this by recording our intervals of decrease. So that includes that left-hand arm, which starts in the sky and goes down to negative 1.823. So the question is, where does it start? Well, it started forever in the x direction, so it's negative infinity. And then we had one other interval of decrease, which was from the high top at negative 0.5 down to 0.823. And that completes the three parts of this function. We graphed it from a table. We located the relative maximum and the relative minima using desmos.com. And then using those 3 points, we highlighted and wrote the intervals of increase and the intervals of decrease using interval notation. All right, so we'll pause at this moment so you can go and work on some of these examples, and we'll come back for our final 2 examples in just a moment. Thank you for joining.